Sometimes when we have a lot of numbers that we want to describe to someone, we like to choose just one number that somehow captures all of them. And we do that by taking an average. And that idea is useful in probability too. So just to remind you, a weighted average of numbers, say x1, x2 through xn, is a number of the form p1 x1 plus p2 x2 up to pn xn, where p1 through pn are non-negative numbers and they sum to 1. So one special case of a weighted average is an ordinary average, where we just let all of these numbers be 1 over n. So we add up the numbers x1 through xn and just divide by n. Now in probability, let's let x be a random variable. And we define EX, which we call expected value of x, to be the sum over all values little x, such that the probability of getting that value is greater than 0, x times the probability. So this is a weighted average of possible values of the random variable capital X weighted by how likely they are. That is, weighted by our probability. So for example, we'll start off with a simple example. Now that we're doing expected value EX, I have to be careful with examples and make sure that capital E little x doesn't look like expected value of x. So example, let's say we roll a die and x is the outcome. The expected value of x is the sum of all of the possible different outcomes, each one weighted by its probability. So 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. So basically that's the sum of the numbers 1 through 6 divided by 6. And on top we have 7, 7, 7, 21 over 6. And if we divide top and bottom by 3, I guess that's 7 halves. Or 3.5. And 3.5 is the ordinary average of the numbers 1 through 6. It's the best single number description of those 6 numbers that we can come up with. Alright, let's do a harder example now. let's roll the die until we get a 6. And let's let y be the number of rolls required. Now y is a discrete random variable, but it has infinitely many possible values. So expected value of y is it could take one roll with probability 1/6. It could take 2 rolls with probability fail, succeed 5, 6, 1, 6. It could take 3 rolls with probability fail, fail, succeed. And I guess it will take n rolls with probability we're going to fail n minus 1 times and then succeed once. So in other words, this is the sum as n goes from 0 to infinity of 5, 6 to the n minus 1 times 1/6 times n. Alright, now what does this turn out to be? Actually, I think for me, it might be easier to analyze it with the numbers written out here. We've got 1/6 everywhere, so I think I'll factor that out. 1/6, and then we have 1 plus 2 times 5, 6, plus 3 times 5, 6 squared, plus 4 times 5, 6 cubed, etc. And then what is that? That looks a little bit like a series I remember from calculus. So let's see. If we add up all the powers of r, where r is a number between -1 and 1, then that's 1 over 1 minus r. And then 1 over 1 minus r squared is the derivative of that, or we could square the power series. And that ends up being 1 plus 2r plus 3r squared plus 4r cubed, etc. All of this is equal to 1 over 1 minus r squared. At least these hold for r between -1 and 1. So let's see what we have here. 1 plus 2 times something plus 3 times something squared plus 4 times something cubed. It looks just like that. And our something is a number between 0 and 1. So it's in the range where this series converges to that fraction. So the expected value of y equals 1/6 of 1 plus 2 times 5, 6 plus 3 times 5, 6 squared plus 4 times 5, 6 cubed, etc. And then by the formula up there, this is 1/6 times 1 over 1 minus this number, 5, 6. The bottom part squared. So it's 1/6. 1 minus 5, 6 is 1/6. So 1/6 times 1 over 1/6 squared. So 1/6 squared is 1 over 36. So this is 1 over 6 over 36. 1 over the fraction is its reciprocal, 36 over 6. So it's 6. So in some sense, if we were to roll a die until we get a 6, we would expect it to take 6 rolls. Not because of the number 6, but more because of the 6 sides of the die. If we were to roll a die until we get a 2, we'd expect that to take 6 rolls also. Because of course getting a 2 happens with probability 1/6 on any roll. Alright, now let's do a different example that doesn't involve toys like dice or coins. This one basically involves collecting data, and a lot of expected value is related to collecting data. So, for example, at a certain university, let's say 3 professors teach probability. And let's say they have 10, 20, and 30 students in their classes. And there are 3 classes because each professor teaches 1 class. If we choose a professor at random, let's let X be his class size or her class size. And if we choose a student at random, let's let Y be his or her class size. Now I claim that the expected value of the student's class size is greater than the expected value of the professor's class size. Well, how could they be if they're the same classes? Well, the difference is choosing a professor at random and choosing a student at random. So, choosing a professor at random is sort of an easier problem. So we've got the different values that the class size of a professor could take are 10, 20, and 30, each with probability 1/3. So 1/3 10 plus 1/3 20 plus 1/3 30 equals 10 plus 20 plus 30 all over 3. 60 over 3, which is 20. And what's expected value of Y? Now there's, I guess, 60 students altogether taking probability, assuming nobody's in 2 classes. So 10 out of the 60 students are going to say their class size is 10. And then 20 out of the 60 students are going to say their class size is 20. And 30 out of the 60 students are going to say their class size is 30. So we can cancel zeros all over the place here. So we've got 10 plus 2 times 20, 10 plus 40, plus 3 times 30, plus 90 over 6 is the expected value of Y. So that's 140 over 6, which is greater than 120 over 6, which is 20. So indeed, the expected class size of a student is smaller than the expected class size of a professor. And And the reason that is if we ask all the students, what is your class size? We're going to be asking half of the students, 30 out of the 60, what's your class size, and they're going to give us the largest number. Whereas only 1/6 of the students are going to give us the smallest number, 10. So if we choose a student at random, we're going to hear the larger number more often, and that's going to cause the expected value to be greater. Whereas if we choose a professor at random, or if we ask all the professors and average their answers, we're going to hear 10 exactly once, 20 exactly once, 30 exactly once. So the three classes are going to be treated equally, rather than the bigger class being weighted more heavily because we're weighting by the number of students in it. The end.